Hello guys, so we are going to continue the discussion with respect to simple linear regression. Now we have already seen the theoretical intuition. Now we'll try to do the practical implementation. Initially we'll go with Jupyter Notebook and then we'll also create end-to-end project with deployment after we complete all these algorithms like simple linear regression, multiple linear regression and all. Okay. So for this example, since I really need to show you a basic way of like how you can probably create a model or how you can train a simple linear regression model. So for that, I'll be taking this particular data set, weight and height. Okay. So over here, our main aim is basically to train our model based on this weight and height. So my model should be able to predict the height if I'm probably giving the input as the weight. So initially this is my data set and I've taken a very small data set just to make you understand. I've created this manually with my hand. Over here, the weight will be the independent feature and your height will be the dependent feature. Okay. So let's go ahead and see how we can probably go ahead and implement, probably train a model by using this specific data set. So initially, as usual, I will be importing some libraries. So here are all the libraries that will be requiring: pandas, matplotlib, numpy and all. Okay. So I will go ahead and execute it. Okay. So the next thing is that I will go ahead and read the data set. And reading the data set is quite easy. I will just write pd.read_csv. And here I am going to basically write height weight.csv, right? And probably if I go and write df.head, I will be able to see the records over here, right? You have to make sure that in the resources, right, I'll be giving you this CSV file and this IPynB file. You have to probably upload in the skill lab and then pw skill lab, and then you have to probably execute it. Okay. So now I have read the data set over here. Let me just show you that how this data set looks in a scattered plot, because first of all, we'll have a scattered plot. Remember, these are like two dimensional, only two features are there, one independent, one dependent. So we can definitely plot this in X and Y axis. So for doing that, I will write plt.scatter. Okay. And I will write df of weight. Okay. Comma df of height. So I'm just trying to plot my weight and height in a scattered plot. And here I will go ahead and write x x label, which is nothing but it is basically my weight, and my y label will basically be my height. Okay. So here we go. Now let's go and see this. So plt, okay, plt.y label. Now if you probably go and see this, see, this is the weight, okay, and this is the height. And this is how my data points are plotted. So these are the same data points which we saw over here. Okay. We have this weight, height, right? We have this 45, 120. So it may get plotted somewhere over here, 45, 120. Then all the points are basically getting plotted. Now our main aim, again, understand what is our main aim. Okay. Our main aim is to basically create a best fit line, right? So if I probably say I have to create a best fit line like this in such a way that if I probably try to find out the differences, right? Or let me just create it in a better way so that you'll be able to understand the line. Our main aim by taking this particular data set is that we should be able to create a model wherein we get a best fit line, which looks something like this. Okay. So it'll be something like this. Okay. Best fit line. Now this best fit line, what will happen? It'll be in such a way that if I probably try to calculate the differences between this actual point and the predicted point, if I do the summation, it should be minimal. Okay. So this is what we are basically going to do. Okay, the line has not been created properly, but don't worry, I will create the line and show it to you by using Python programming language. Okay. So this is what we are going to do. Now, always understand whenever we start our machine learning algorithm, right? Whenever we want to train our machine learning algorithm, there are some steps that we really need to do. Okay. So what are the steps? I will just create a notepad file. Okay. The first step is that I have my data set. Okay. Now in the second step, what we do the train test split of the data set. Okay. Of the data set. Now train test split of the data set, how do we do it? It is very much simple. I will go and search for sklearn. Now why do we do train test split? Okay. I've already explained you in the feature engineering. The train test split is basically required so that we can train our model with the training data set and we can test our model with the test data set. Okay. So for doing the train test split, I will be using model selection. So here you have sklearn.model selection, and then I will go ahead and import train test split. So first of all, before doing train test split, there is also one more very important thing. Before this, I will divide my data set. Okay, I will divide, or I will divide the features based on independent and dependent features. Okay, dependent, you should be knowing which are your independent and dependent features, right? So we'll divide the features based on this. Okay, the independent feature, you know what it is, because we are going to take weight as an independent feature, and height will be my dependent feature. So in order to basically take that, what I'm going to do, I will go to write over here, divide my data set, divide our data set, since you are also executing. Okay, our data set into independent and dependent feature. Okay, so this is the task that we are doing. Now for the independent, I will write df of weight. Okay, df of weight. Now understand, this x variable will basically be treated as an independent feature. It is a good practice you try to write it as x, because many researchers, where we probably see the coding in books, in different books, right? They specifically use this notation of x, right? So x will basically be having my df of weight. Okay, and y, which will be small y, this will be my, this specifically is my independent feature. Okay, independent features, right? And if I probably write df of height, this will be my dependent features. Okay, so right now only one are there, so I'll write feature. Okay, so once I execute it, so this will be basically my x, and this will be my y. Okay, so you can probably go and see x and y. Perfect. Just a second. Okay, now what we are going to do after this, okay, and I'll go back to my notebook over here. Now we'll train test split of the data set based on this independent and dependent feature. So for doing that, I will be importing from sklearn dot model selection import train test split. Okay, so we are going to basically use this train test split library to do the train test split itself, right? Always remember, the training data will be used for training our model. Okay, now in order to do this, I will probably write xtrain. So train test split gives 4 parameters. One is for xtrain, the other one is for xtest. Okay, and I can write my own variable name, it is up to me. Then this ytrain, and then you have ytest. Now understand, I will be using xtrain and ytrain. See, xtrain is my input feature, ytrain is my output feature for the training data set. Okay, so xtrain, again I'm repeating it, xtrain is my independent feature, ytrain is my dependent feature for the training data set. So for training my model, I will be taking xtrain and ytrain, right? For testing our model, we'll take xtest and ytest, right? So this 4 variables is basically returned by this train test split. Okay, now inside this train test split, the first parameter will be my x value, then second parameter will be my dependent feature y value. The third parameter, I will go and specify my test size. So this will be nothing but 0.20. 0.20 is basically saying that 20% of the data points in this x, right, it will be considered as the test data. So if there are 100 records in x, out of that, if I write 0.20 as test size, then 20 records will be put in the test data. Okay, and remaining 80 records will be used in the training data for training the model. Okay, and then I will also make sure that I will initialize one random state. The reason why I'm initializing the random state is that because let's say I've put this random state value, this is just like a seed value. Okay, if I put this, the type of train test split, right, will be like if you also put the same random state value, then our split will be almost same. Okay, so now once I execute it, so now you can basically see, before my x dot shape was having 23 records, right? Total 23 records. Now if you go and see my xtrain dot shape, you will be seeing only 18 records. Remaining 5 records are the 20% of a record, and it will be available in xtest data. So xtest dot shape, you see xtest will be, sorry, xtrain. Okay, So if you, xtest.share. So here you can see 5 records is placed over here for testing the model, and remaining 18 records is placed here to train our model. Similarly, with respect to ytrain also, you'll be able to see ytrain.shape. Here you can see 18 records are there in the ytrain. This is the output for these records. Okay. And similarly, if I probably go and write ytest.shape, the remaining 5 records output will be over here, right? So this is super, super important. You have to do the train test split. So here I'm basically going to write the train test split, train test split. Okay. Important step altogether. Okay. Perfect. This is done and we are good to go. Now let's go to the next step and let's see what we are going to basically do. Now the next step after doing the train test split, we will standardize the data. Okay. Now standardizing the data will be important. Why? Because understand, in this, the feature of height, right? Weight is calculated in different unit, height is calculated in different unit. And if you probably go and see this plot also, right? Now weight is ranging between somewhere around 40 to 100, right? Now we need to scale down this data so that our gradient descent optimization will happen quickly. See, if I am having this very big value between 40 to 100, what will happen? Every time I have to go ahead and calculate my cost function by calculating the best fit line, finding the error. So while we are finding the error, there will be a bigger number. So if we scale down all this weight value in a standardized format and then probably train the model, right? So in that way, we will be able to quickly optimize or converge in the gradient descent. Okay, so that is the reason we really need to do standardization. Now it is not that standardization needs to be performed in every algorithm. Wherever there is distance based algorithms, wherever there is optimization kind of algorithms, there will be specifically using. Going forward, I will be telling you where standardization, which all algorithm standardization will be applied. In linear regression, yes, standardization needs to be applied. So now we will go ahead and standardize the data set. Okay, specifically over here, my train data. Okay, not the output feature, only train independent feature. Okay, independent feature. Okay, independent data. So for doing this, again, for standard scalar, I hope everybody knows this. We have discussed this. Dot pre-processing, I will be importing it. So sklearn.preprocessing import standard scalar. Okay. So once I will execute it, this standard scalar is nothing but we are just applying the z-score formula, if you remember, right? So now if I go ahead and write scalar as standard scalar, this will be what we are basically initializing. So this is my scalar itself. And now there are two important things, right? Since I have training data and test data, we need to standardize our test data also based on the observation that we have got from the training data. So if I go ahead and write scalar dot fit underscore transform on xtrain, right? So if I go ahead and write fit underscore transform on xtrain, so what will happen? It will give us a value, right? It will go and compute what is the mean, what is the standard deviation of xtrain, and then it is going to change the value by applying z-score on every data point of x, right? Xtrain. So if I probably go ahead and execute it, you'll be able to see here I'm getting an error. Let's see what is the error. Okay, it is basically asking for a 2D array. Not a worries. I will just reshape this. If I probably see that, right? This is xtrain, right? Okay, no worries. So I will do one thing. I will just write something like this. df of weight. I'll make it as 2 dimension. So now let me go ahead and do this. So here I have now 18,1. This basically indicates that I have one column, 18 data points, right? So the same thing will basically happen with xtest.shape. Yeah, 5,1. And then here I have 18, and 5, this is with respect to output feature, right? Ytrain is with respect to the output feature. Here I'm just making it as 2 dimension. 2 dimension basically means one column, 18 records, data points. One column, 5 data points. Okay, now it will definitely execute. Now if I do fit underscore transform on xtrain, so this is what I will be getting, right? So this will be my xtrain data point, which is in the standardized format. So here I'm going to basically write it as xtrain. Now what is happening in this fit underscore transform? First, I will go and apply z-score in every data points of xtrain, right? Every data points of xtrain. So if I probably go and see my xtrain over here, right? Dot head, I'll just see the top 5 records. Let's see. So every data point over here, what will happen? Z score will get applied on this. And in order to find out the Z score, we require the mean and standard deviation of X train. So fit will compute the mean and standard deviation of X train, and transform will go ahead and apply the Z score formula on every data points, right? So I will go and store this in X underscore train. But for X underscore test, we don't need to write fit underscore transform. We will just write dot transform. The reason we are doing this is that we don't need to again calculate our mean and standard deviation. The mean and standard deviation that is utilized in the Z score, it is basically being used from this X underscore train itself, right? So again, let me repeat it. Now, what exactly is basically happening over here? Okay, let's go and understand this in a proper way. Okay, so initially I have this X underscore train data. Okay, and this is X underscore test data. Let's say I have some values like this. Okay, now considering these values, when I do fit underscore transform, that basically means the fit first will calculate the mean and standard deviation for this data, right? Then transform will do what? It will try to change this data by applying the Z score formula, right? Now for the X test data, what we are basically going to do is that for this X test data, when we directly say transform, then the Z score that is basically getting applied, right? It will be using this mean and standard deviation of the X train, right? And then it will take this data point, it will subtract with this mean and standard deviation. The reason we do this, because there is a concept of something called as data leakage. So a dedicated video will come on data leakage, but just understand that for the training data, we need to do fit underscore transform, and for the test data, we need to do just transform, right? The reason why I'm doing this, my model should not know anything about the test data, right? It should just have the information about the train data. Okay. So once I probably go ahead and execute, now I'll be getting my X train and Y train in the standardized format. Now this is perfect. Now if you probably go and just write plt.scatter, and if I probably just plot this X train and Y train, you'll also be able to see my data points, X train comma Y underscore train. Okay. So this is how my data points looks like. Now you see all the values is ranging between -1.5 to +1.5. It has been scaled down. Okay. Now let's go ahead and train our model. Train the model. Okay. And which model we are going to train? It is a simple linear regression model. Why simple linear? Because I just have one feature, right? So here I'm going to basically train my simple linear regression model. Now in order to train this specific model, what I'm actually going to do over here is that we have to go and see from where we can probably get this model. So here in sklearn, you also have a linear regression model. Okay. So this is the library that I'm going to use for performing the training of the linear regression. Okay. So here I have this sklearn.linear model. I'll be using this linear regression, and there is a parameter which is called as fit intercept is equal to true. So which will help us to calculate the intercept. And here you can also see some of the examples. In short, this model will now be responsible in finding the best fit line and also all the slopes of the independent feature. Okay. So theoretical intuition, we have already understood how they are going to do, what cost function they are going to use and all. So here I'm going to go over here and let's go ahead and initialize. So I will write from sklearn dot linear model, and we are going to basically import linear regression. Okay. Now this is the first step, right? So what all things we did, right? Over here we standardized the data, and then we are training the model, okay, using linear regression. This is what we are doing, right? Perfect. Over here, now I will go ahead and execute this. Now I'll go and first of all create my regression object. So this will be my regressor object, and here I will initialize it to linear regression. So by default, once I execute it, whatever is the parameters that is set, that is going to get considered. Okay. Now after you do this, now again, in order to train my data, I will just write regressor.fit on my X train and Y train, right? So this is my independent feature. This is my dependent feature. When I do regressor.fit on X train and Y train, and once I execute it, now this is going to find out all the points, right, with respect to different theta 0 value. Like theta 0 is nothing but intercept and the slope, right? Slope is theta 1. Okay. Now observe one thing over here. Once we do fit on X train and Y train, this is basically trained on this particular data set. Okay. Now if I go ahead and write regressor dot, there is something called as coefficient. Now how many different slopes we will be getting? See, there is only one independent feature, right, over here, and there is one dependent feature. If I have one independent feature, I will just have one slope. So if I write regressor dot coefficient, then here you will be able to see this is basically my slope, 17.034. Okay. So if I want to print it, print, and I will write the slope of weight, slope or coefficient of weight, or coefficient of weight is this specific value, right? That is regressor dot coef, right? So I will just go ahead and execute it. Now I hope everybody is clear with this, right? This is basically my coefficient, right? Similarly, I can go and print my intercept also. Intercept will basically be given in the form of, okay, intercept will be given in the form of something like regressor dot, there will be something like intercept. So finally you can see intercept, I'm getting it as 157.5, and the slope of the coefficient of the weight or the coefficient of weight is nothing but 17.03, right? Now let's create that best fit line by using this coefficient. Okay, so what exactly is happening over here? I will just give you a simple way of understanding. If I now go ahead and plot, see, plt dot scatter on X train comma Y train, and if I execute it, okay, so here you'll be seeing this is how my data points looks like. Now if I want to create the best fit line, how do I create a best fit line? Very simple. I will just say plt dot plot. Okay, and first of all I will definitely have my X train data. Now remember that formula, h theta of x. See what will happen now. I will just execute it and show it everything to you, don't worry. Okay, so my h theta of x is nothing but theta 0 plus theta 1 into x1, right? So theta 0, you know what is theta 0? Theta 0 is nothing but 157.5, which we got it from here. Theta 1 is nothing but 17.03, right? Now what we are going to do, for every x of I data points, I'm just going to apply it over here and probably get my h theta of x value. So here you'll be able to see that I will be getting something like this kind of best fit line, okay, for all the x points. And then finally I'll be constructing my best fit line by just plotting it in a straight line. Okay, and that is what we are basically going to do. Okay, so let's see this, how to basically do it. Okay, so I will go over here. Now I'll write x underscore train. Now in order to do the prediction by using this theta 0 and theta 1 value, I will use the regressor object and just write dot predict on my X train data. So once I do this and once I execute it, here you can see I'm getting the best fit line. Okay, let me use some other color. So I hope there is something called as color plt dot plot. Let's see. I'll press shift tab, plt dot, and I can use r plus. Okay, so I will use something like r plus. Now here you can see these are the dotted lines that I'm getting, right? And this is for the prediction, right? So if I probably just write r, here you'll be able to see this is how our straight best fit line is basically coming. Now I hope you are able to understand, right? Like how a best fit line is basically created, right? We simply did the prediction on the X train data. We just applied that formula, h theta of x is equal to theta 0 plus theta 1 into x. Theta 0 was nothing but 157.5. Theta 1 is nothing but 17.034. So for every x data point, we went ahead and just calculated h theta of x, and finally we got this entire best fit line. Okay. Now, so much theoretical intuition we discussed, right? At the end of the day, our main aim is basically to create a best fit line, right? Now, this was a scenario wherein we just have one independent features. Now, how do I do now see this, I will write over here, very important, okay? And I'll copy this, it will be helpful for you. So over here, prediction of the train data and prediction of the test data. See, observe over here. Prediction of the train data. So predicted height output is nothing but intercept plus coefficient multiplied by the weights. So whenever we write try to do the prediction, right? It will be this intercept plus coefficient multiplied by this value, right? So in this case, you will be able to see what is the intercept that I got, 157. So if I probably go and see this, just a second. Okay, if I go and probably put it over here, so this will be 156. And if I go and see my intercept, it will be 17.03. So perfect, we are here, right? Similarly, I will copy this over here and execute it. Now for the prediction of the test data also I have to do the same thing, right? So let's go ahead and do the prediction for the test data. So ypred underscore test. I'm just going to use the same regressor object dot predict on my x test data set, right? So once I do this, you'll be able to see this will be my predicted output, ypred underscore test, right? This is my predicted output. And if you also want to see what is your real output, so I'll just make this as a small letter, okay? And if you want to probably see what is your y test is your actual output, right? So now we can compare these two and we can basically calculate the accuracy. That is what we can basically do. Say for the 5 data points, right? I got this as 161, this as 161.08, this is 171. Sorry, 177 is the actual test output, right? Now what we can do, we can again do this plotting, something like this. So here I will write. First of all, test data is basically used to test how good the model is, right? So if I go ahead and write y underscore test and again x underscore test and we do regression.predict on x underscore test, you'll be able to see how my best fit line will probably come. So this is how the best fit line is basically coming. And these are all my predictions that I'm able to get, right? In a straight line, these are my actual points. Now what we can do after doing the prediction, we can compare this to, okay, data points, find out the difference. And based on that, we can compute our performance metric score, that is R square and adjusted R square. Still, we have not discussed R square and adjusted R square. That we will probably discuss as we go ahead, okay? But I hope you got an idea about it, like how we can perform a simple linear regression. So let's go ahead and compute the R square and adjusted R square with respect to this, okay? So in the performance metrics, now I have my y test. See, performance metrics, okay? Now in the performance metrics, I can definitely show you 2-3 things over here. We will be focusing on calculating MSE, mean squared error, MAE, mean absolute error, which we have already discussed, and one more, that is RMSE if you want, that is up to you. And then we'll also try to see R squared and adjusted R squared to just see the model performance, adjusted R squared, okay? We'll just see the model accuracy, okay? So all these things we will be doing, and here let's go ahead and execute it. Now in order to use MSE, MAE, RMSE, right, what we will be doing is that we will again be using sklearn. So in sklearn, if you write MSE, okay, so here you have this MSE, that is mean squared error. Automatically when you call this function, that formula which we have actually discussed about will get applied, okay, to calculate the cost function. Now with respect to this is basically present in sklearn.metrics. So what I will do, I will say from sklearn.metrics, I'm going to import, okay, mean squared error. So sklearn, okay, so spelling is wrong. So sklearn mean squared error, okay. Then I will also go ahead and execute mean absolute error. So both of this and root mean squared error is nothing but we'll try to just find out the square root of MSE. So once I execute this, then in order to calculate the MSE, I will just use this mean squared error. And here I'm going to use my y test data just to check the performance. This is my real data point and my predicted data point, which will be ypred underscore test, right? So this is what my model has predicted. This is what is the real value. And we are trying to compare and finding out the accuracy, okay, with the help of MSE, okay. And similarly, MAE is nothing but mean absolute error. And here also I'm going to basically take y underscore test, comma y underscore pred underscore test, right? And similarly, now I will go and write RMSE, which will be nothing but np dot sqrt and here I will be using MSE. Okay, this is what we specifically use for RMSE. Then we can go ahead and print MSE. Okay, we can go ahead and print MAE, and we can go ahead and print RMSE. You know the advantages of using MSE. You know the advantages of using MSE, MAE, right? We have all discussed this. So here you'll be able to see that I'm getting the mean squared error as 109. This is 9.8 and this is 10.477. Now the more, the less the value of this is, the more better your model is, right? So that kind of scenarios will definitely, you'll be able to see that as this value keeps on decreasing, that basically means your model is performing even much more better. But still, if someone asks you how to calculate basically how much good your accuracy of the model is, so for that we specifically use something like from a scalar dot metrics, and here I'm going to import R squared. Okay, R2 score. So this R2 score over here is nothing but I will be using R2 underscore score, and here I will be giving y test again, and this will also be my y pred. And you know how to compute this, right, with respect to y test and y pred test. Okay, so once I go ahead and execute, now I will be getting my score, and this score, whatever I'm getting, I'm basically getting 77.6% accuracy. Okay, if you want to know the formula of this, I've already spoken about the formula over here. So let me quickly go ahead and write the formula over here. So this will be my markdown. Done. So this is how the formula is for the R square. Now for the adjusted R square, if you know, my formula will look something like this, right? So if I go and see this, and we have discussed about all these things, right? Adjusted R square. We are just trying to find out what is the accuracy of the model. Okay. So markdown, great, adjusted. Okay. Perfect. And here you have this. This will also be a markdown. So this is the formula for the adjusted R square. Now what I can basically do, I will just go ahead and write something like this. 1 minus score. Score is nothing but R square. Length of y test minus 1, which is nothing but n minus 1. And then you have n minus k minus 1, right? This k is nothing but number of predictors, and then minus 1. Whatever will be that, I will be getting my R square, adjusted R square value. Always remember, your R squared value will always be greater than adjusted R square. This is what we had also discussed. So great, your adjusted, your R square is basically coming as 77.69%. This indicates that your model is 76.69% accurate. Your adjusted R square is this much. Your MSE, MAE, RMSE is this much. This is basically talking about how much error is still left with respect to your model when it is doing the prediction for the test data. And the remaining all we have specifically done. We have done the prediction of the trained data, test data, everything, and all the steps we have basically followed, right? So this was just an example with respect to simple linear regression. And here we have just not, done only one or two things. We have done many things as we have gone ahead. Now, one very important thing that I really want to talk about is that what are the assumptions? When do you say you have actually trained a very good regression model? Okay. So that assumptions that I really want to talk about, first of all, okay. Now, before this, this is your object, right? So this regressor is basically your linear regression model, okay. Now, with respect to linear regression model, whenever you get a new data point, let's say I'm getting a new data point. So new data point, I'm getting it. Let's say the weight is 80, okay. I want to do the prediction for 80. Okay. So how do I go ahead and do it? So first of all, I will go and write weight, or I can write scaled underscore weight. And this weight, right? If I want to do the scaling, then what I will do? I will just use this same standard scalar. So standard scalar. Okay. Dot, I have to first of all transform this value. So what I will transform? I'll transform 80, right? So once I probably transform it, and if I go and see my scaled weight, and we have to do this, right? First is we need to find out the scaled weight. I'm getting an error. Let's see what is the error. It is basically saying that to give a 2D array, not a problem. So I will give it something like this 2D, right? So now if you go and see my scaled weight, it is nothing but 0.325, right? Now this value I have to give for my prediction, okay? Now if I wanted to give this value for the prediction, then what will happen? I will be using regressor dot predict, and here I will basically give my scaled weight, and I will do the prediction. So still there is an error. Found array with 4 dimension. Why found array with 4 dimension? Because okay, scaled weight. Okay. Scaled weight. I'll do one thing. I will remove this. Okay, and I will write scaled weight. Let's see, and I will give of 0. Okay, so let's see. Again, still I'm getting an error. Okay, now I'll give in the form of 1 dimension, 2 dimension, right? So once I execute this, now you can see that the prediction for the 80 kgs, the height is nothing but 163, right? So I can probably write over here print. Okay, print. So here why that error was coming, because I had just given it as a 1 dimension, right? So always understand, while training our model, when we did fit underscore transform over here, right? Or when we did fit, you'll be able to see when we did fit, right? This X train and Y train, X train is specifically 2 dimension point. Okay. So similarly here also we need to give the 2 dimension. So that is the reason why I've used this additional square braces, and then this scaled weight of 0 is specifically giving me this value. Okay. So if I go and execute this, and if I write scaled underscore weight of 0, will basically give me this array value. Okay. This is also 2-dimensional output that we are probably getting. So this is what is the output. So here I can basically write print the height prediction for weight 80 kgs is whatever value we are getting over here. That will basically be my output. So it is nothing but 163.01. Okay. Great. We have done this. Now let's go ahead and talk about some of the important assumptions. When do you say your model is really performing well, right? What kind of assumption is required in the simple linear regression? And remember, this will get applied to multiple linear regression also. That is the reason why I'm explaining like this. So first of all, we will plot a scatter plot for the prediction. So if I plot the scatter plot for the prediction, so how do I plot it? It is very simple. plt.scatter, and then first of all, I will take y underscore test, which is my real data point. And then I will write y underscore pred underscore test. So once we plot this scatter plot, okay, here you'll be able to see that this scattered plot will be linearly available over here, linearly distributed. If it is linearly distributed, just consider that, yes, you have done a very good predictions. Okay. So with respect to this, you will be able to see that, yes, you have actually done a good prediction. And that is the reason you are getting a linear way of distribution of your y underscore test and y underscore pred test. Okay. Next thing, this is my first assumption. The next assumption is regarding residuals. Now, what is exactly residuals? Residuals is nothing but this is the difference between y test and y underscore pred underscore test, right? So y underscore test and y underscore pred underscore test, right? Once I find out the difference between the actual point and the predicted point, I'm going to basically get the residuals. So if I probably go and see what is my residuals over here, you'll be able to see these are my residuals for every point. Okay. Now, if I plot this residuals, the second assumption, if we plot this residuals, how do I plot this residuals over here? I will just say import cbon as SNS, and here I will write SNS.dist plot, okay, or histogram plot, whatever plot you want. And if I write residuals with kind is equal to KDE, and if I execute it, cbon, okay, no worries, kind full stop, right? Okay, cbon. Once I execute this, kind is coming as an error. Why? Dist plot, let's see, residuals, kind KDE is equal to true. So I can basically just write KDE is equal to true. Kind was not there. I think it was in the previous version. No worries. So now here you'll be able to see that I will be getting this kind of distribution, right? Now, with respect to this, because we are just trying to plot the residuals, right? And over here, one more assumption that we can definitely make, that if we are probably getting this kind of normal distribution, I know this is a little bit left skewed, but here you can basically see that, yeah, I'm able to get a kind of normal distribution. So my residuals are also ranging between -30 to +30. Here you can definitely come to a conclusion that yes, you are able to create a better model altogether, right? So this is the second assumptions that we specifically use. The third thing is that one more specific thing that I really want to talk about. If we create a scattered plot with respect to predictions and residuals, right? And if I execute this, this should be a uniform distribution, right? Uniform distribution basically means the data points will be available here and there, both in positive and negative side. So this way, this is a distribution is a uniform distribution. We have also studied in the stats, right? And if this follows a uniform distribution with respect to your y-pred test and the residuals, the error that you are able to get, then this is also a very good model as we go ahead, right? So these are some of the assumptions that you need to test whenever you are probably creating a linear regression model, right? So I hope you are able to understand with respect to the simple linear regression. Now in the next video, we'll try to do a multiple linear regression where I'll take multiple features. But I hope you got an idea how to do the prediction, what are the steps you need to follow and all. And this is how you predict the model, okay? What we do for the model, we basically create a pickle file, right? So that step, pickling the model, right? That step I will show it in a multiple linear regression, because this model, right, it will be saved in the form of file and it will be responsible and it will be used for doing the deployment purpose. So this part I will talk about it when we are basically discussing about the multiple linear regression. So yes, this was it from my side. I hope you like this particular video. Yes, I will see you all in the next video. Thank you.